In this video, we're going to discuss confidence intervals. This is sections 5.1 and 5.2. Our first exercise is to find the z-scores corresponding to the graph on the top. Let's start with that one. So we want the z-score where 85% of the data is to the left of the z-score and 15% is to the right. Now you can do this using a z-table or Microsoft Excel. So what we're going to do is we can look for 0.85 in our z-table, or we can use the command equals norm.inv 0.8501, and either one of these will give us our answer. Let's start with the z-table. So this table says standard normal distribution. Table values represent the area to the left of the z-score, and we're going to look for 0.85. Remember that the z-score of 0 is where 50% is to the left of the z-score, so it's going to be bigger than 0. So we're going to ignore all these negatives and scroll down to 0, 0.5. Now let's search for 0.85. So here's 0.84 and this is 0.86, so it's somewhere in between. Okay, this one's really close. 1.03, I get 0.848. This one looks a bit better. 1.04, that's 0.85083. A little bit more than 0.85 is to the left of that z-score. So it's somewhere between 1.03 and 1.04. I'm just going to round it to 1.04. Let's check our answer with Microsoft Excel. Okay, here I am in Microsoft Excel, and in my first cell here, A1, I'm going to type equals norm.inv 0.85. The mean is 0. The standard deviation is 1 for z-scores. And if I hit enter, I get 1.036, which we can round to 1.04. So you can see how the z-table and Microsoft Excel are giving me a very similar answer. So let's say it's about 1.04. Let's look at the second graph. We have that we want to find the z-score where the area to the left is 15% or 0.15, and the area to the right is 85% or 0.85. We can do the same thing we did in the last problem where we look at the z-table and try to find 0.15, or we could use the command norm.inv 0.15, 0, 1. Another thing you can do is you can use the symmetry of the graph. The symmetry of the graph says if the top one is 1.04, then the one on the bottom is going to be negative 1.04 because it's the same distance to the right, and the distance to the right of 0 for that z-score is 1.04. So then the distance to the left, which is going to be the same distance but to the left, that is also 1.04. And remember that when we're to the left of 0, the z-scores are negative, so it'd be negative 1.04. Now, if we put the two z-scores, z is equal to negative 1.04 and z is equal to 1.04 on the graph, then we have 15% of the graph is to the left of the negative z-score and 15% is to the right of the positive z-score. What percentage would go in the middle? Well, 70% would go in the middle because all of these percentages have to add to give us 100%. That's 100% of the graph. Now, let x be a normally distributed random variable, and the mean, let's say it's 0.5, and sigma is 0.2. Then 70% of the time, x will be within what two values? So we want to take the mean and add and subtract 1.04 standard deviations from that mean to get a range of values. So we're going to take 0.5, and we're going to take our standard deviation, 0.2, and multiply it by 1.04, because we want to go just a little bit further than one standard deviation from the mean. Remember that the empirical rule says that one standard deviation from the mean is 68% of the data. But if we go 1.04 standard deviations from the mean, that's 70% of the data. So we want to go just a little bit further than one standard deviation. So we're going to take 1.04 and multiply by our standard deviation. We'll get 0.208. And we're going to add that number to 0.5, the mean, and we're going to subtract that number from 0.5. And we'll get two values. We'll get 0.708, that's going to be the number on the right, and 0.292 is the number on the left. So 70% of the time, x will be within the values 0.292 and 0.708. Let's try another one. Let's find the z-scores corresponding to this graph. I want two z-scores. One of them's negative, one of them's positive, where 5% is to the left of the negative z-score, 5% is to the right of the positive z-score, and 90% of the data is in between. How do we do that? So there's two ways. We can find the negative z-score by using the code equals norm.inv, put 0.05, comma 0, comma 1, or we could look into the z-table and try to find the z-score that corresponds to 0.05. And once you have the negative one, the other one is just the positive value of it. Or you could find the positive one, so you look for 0.95, because remember that the z-table is everything to the left, not to the other z value, but it's everything to the left, which is 0.95 of the data, 95%. So you would look for 95% in your z-table, or you could use that code in Microsoft Excel where you put 0.95 for the z-score. And then once you have that positive value, then the other z value is just the negative of that. And that's what I'm going to do. I'm going to look for 0.95 in my z-table. So here's my z-table. I'm going to look for 0.95. Here's 0.94. So here's 0.949, and here's 0.95. So it looks like to me is 1.6, and up here is 0.4. So about 1.64, or you could say 1.65 is somewhere in between. So let's just say it's 1.645, like halfway, but we can round it. Just say it's this one, 1.65. That's the closest. Let's also check while we're here the negative z-score. The negative z-score corresponds to 5% to the left. So let's look for 0.05. Now this is 0.5. We want 0.05. And it looks like it's right here, somewhere in between these two values, and that's negative 1.6, halfway between negative 1.64 and negative 1.65. Exactly what the positive value we got. Let's also try this with Microsoft Excel. So I'm going to clear this, and I'm going to type equals norm.inv 0.9501, and I get 1.64, or you could round it to 1.65 or 1.64. And if I put in here, instead of the 95, I put 0.05, I get negative 1.64. So here I have put the two z-scores, the approximate z-scores, negative 1.65. And now let x be a normally distributed random variable with mu equal to 0.5 and sigma equal to 0.2. Then 90% of the time, x will be within the values what and what. So maybe pause the video and see if you can find the two values. So we need to take our standard deviation and multiply it by the 1.65. Then we're going to add and subtract that number from 0.5. So I got 0.33 when I multiplied 0.2 with 1.65. And then if I take 0.5 and add 0.33, I get 0.83. And if I take 0.5 and subtract 0.33, I got 0.17. So there's a 90% chance that x will be within the values 0.17 and 0.83. Our next topic is the central limit theorem for proportions. This is a very important theorem, and it's a theorem that we're going to use for the rest of the video. Now, remember that in statistics, there's usually a population that we're interested in, and we want to find out some piece of information about that population. Let's say we want to find the percentage of people who smoke cigarettes, or the percentage of people who have high cholesterol. Whatever percentage or proportion you're trying to find, we call that P, just the letter P. And because it's going to take too much time and money to find that, we create a sample and we find the sample proportion P hat. Now, suppose you conduct a study and find a sample proportion P hat. You want to construct a confidence interval for the true population proportion P. That means you want to build a set of values around your sample proportion that you feel you're very confident contain the real P. We'll never be able to find the real P, but we can give out a range and say we believe it lives in that range. That's what a confidence interval is. Now, in order for us to create a confidence interval, we need to make sure our sample is sufficiently large. Recall that a sufficiently large sample is where we take our sample size and multiply it by the true population proportion. We see n times p, we see if that's greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. But in this case, we don't know what the true p is, but we have the next best thing, which is p hat. So we're going to take n times p hat and n times 1 minus p hat and see if both of those numbers are greater than or equal to 10. If they are, then we have a sufficiently large sample and we can continue. Now we're going to construct our confidence interval. 90% of the time, the value of the true P will be within the range P hat plus or minus 1.65 times the standard error. Remember in the last example how I got this 1.65 for the z-score? Because 90% of the data was between negative 1.65 and 1.65, those two z-scores. And what we did when we were trying to find a range around mu is we took mu and added and subtracted 1.65 times sigma. Well, we don't know the true mu here, or the true p, and we don't know the true standard deviation. So we're using p hat, and we're going to add and subtract 1.65 times what we call the standard error. For the 95% of the time, the true P will be within the range P hat plus or minus 1.96 times the standard error. Now, 1.96, where did that come from? That's really close to 2. And if you remember from the empirical rule, that there's about a 95% chance that we're within 2 standard deviations from the mean. This is just a little more precise. It's really closer to 1.96. The empirical rule was an estimate. 98% of the time, the value of the true P will be within the range P hat plus or minus 2.33 times the standard error. You can check this and see using your z-table where I got that number 2.33 from. It's very similar to what we did earlier when we found the number 1.65. Now the equation for the standard error is square root n times p hat 1 minus p hat. And you may recognize that part from when we talked about how the normal distribution and the binomial distribution were similar. It's the same formula. The only thing that's different is I'm dividing by n because we're working with percentages and not actual people here. So when we work with percentages, we have to divide by n. Now, when we take the standard error and multiply by the z-score, we call this the margin of error. How far away we can be from our estimate p hat. Let's try a problem. Suppose we take a poll of 1,000 American adults and find that 84% of those 1,000 adults own a smartphone. Can you construct a 95% confidence interval for the true percentage of American adults that own a smartphone? So the first thing we're going to do is see if we have a sufficiently large sample. Now to do that, we're going to take the sample size 1,000 and multiply it by the success probability, 0.84, and we get 840. And then if we take the sample size 1,000 and multiply by the failure probability, we get 160. And both of those numbers are bigger than 10, so we can keep going. The standard error, let's calculate that next, is the square root of n times p times 1 minus p, all divided by 1,000. Make sure you don't put the square root, include that 1,000 in the denominator in the square root. It doesn't go in the square root. So if you're putting this into a calculator, double check. Start with the top, hit enter, and then divide by 1,000. So you don't get that 1,000 in the bottom under the square root. And I got 0.012. Now we can build our confidence interval. For 95% confidence, we set the z-score. If you go back, we'll go back to the slide real quick. 95% confidence, the z-score that goes in front of the standard error is 1.96. We said it was about 2 standard deviations away from the mean. So I'm going to take that 1.96 and I'm going to multiply it by the standard error. I got about 0.023 when I multiplied those two numbers together. Then I'm going to take the 0.84 and add and subtract the margin of error, the 0.023. When I subtracted it, I got 0.817, and when I added it, I got 0.863. Double check that these numbers are correct. Now let's summarize our findings in the context of this problem. We are 95% confident that the true percentage P of American adults that own a smartphone is between 81.7% and 86.3%. What does it mean I'm 95% confident? That means if I did this 100 different times, if I created a sample of 1,000 adults and found a p-hat for each sample, that 95 times out of 100, the true P will live in the confidence interval that I created. So, for example, here I got, for this particular sample, I got 84% had a smartphone. My next example, I could get 82%, or I might get 90% had a smartphone because they're different samples. And for each one of these, I can construct a confidence interval just like I did here. And not all of them may have the true P. We would expect that if we did this 100 times, 100 different samples of 1,000 adults, that 95 of them would have the true P living in that confidence interval. So this may be one of the times out of 100 where it doesn't live there. So that's why we say we're not 100% sure that this has happened, but we're 95% confident that the true P lives in this confidence interval. Let's try the same example, but let's change the confidence level. So instead of 95%, let's make it 98%. So before we continue, what do you think will change? How will that confidence interval change? Do you expect it to get wider, or do you expect it to get more narrow? There'll be less values in between the two numbers we'd find in the confidence interval. So if you were more confident about something, that means you're more certain. And to be more certain, you need a bigger range, a larger range of values. So the confidence interval is going to become wider. Let's see. So the only thing that has changed in this problem is the confidence level. So the number of adults is the same, and the p-hat is still the same, 84%. So n times p and n times 1 minus p-hat are still going to be the same. And the standard error is still going to be the same. The only thing that's going to change is the number that we multiply the standard error with. The margin of error is going to change, and that's going to get a little bit bigger. So what you need to do is get a calculator, and remember that this 2.33 came from that slide where I said 95% of the time is between these values, 98% of the time is between these values. And you can just go back in the video a little bit and you'll see it was 2.33 was the z-score that corresponded to a 98% confidence level. So we're going to take 2.33 and multiply by 0.012. And if we add it and subtract it, we'll get the numbers 0.81 and 0.87. So we are 98% confident that the true percentage P of American adults that own a smartphone is between 81% and 87%. Notice that this interval is larger than in the last problem. It's just a little bit bigger, and that's because we're more confident. Let's try a new example. A survey of 2,306 adult Americans aged 18 and older, conducted by Harris Interactive, found that 417 of those adults had donated blood in the past 2 years. First part, and I want you to pause the video, is I want you to obtain a point estimate for the population proportion of adult Americans aged 18 and older who have donated blood in the past 2 years. So I got 0.181, or about 18.1%. I just took 417 and divided by 2306. Now let's verify that the requirements for constructing a confidence interval about p hat are satisfied. All we need to do is take the number of people in the survey and multiply it by p hat. So I took 2306 and multiplied it by 0.181, and I got 417, which was the number of successes in the problem. And then I took the n, 2306, and multiplied by the failure probability, and I got about 1889, which, remember, if we have 2306 adults and 417 of them are successes, then 1,889 of them have to be failures. So if both of those numbers are greater than or equal to 10, so we can continue. Now let's construct a 90% confidence interval for the population proportion of adult Americans who have donated blood in the past 2 years. Pause the video and see if you can create the confidence interval. So remember, you need to find the standard error, you need to figure out the z-score, and I believe that for 90%, I gave you that earlier. And so then you need to find the margin of error and add it and subtract it from p hat. So the margin of error is taking 1.65 and multiplying it by the standard error, which is the square root of n times p times 1 minus p. So you see I have n is 2306, p is 0.181, and 1 minus p is 0.819. I find the square root of all of that, and then I divide it by 2306. So I'm going to take that number, multiply it by 1.65, and I got that the confidence interval is somewhere between 0.168 and 0.194. So now let's interpret the interval in context of this problem. So we are 90% confident that the true percentage P of Americans aged 18 and older who donated blood in the past 2 years is between 16.8% and 19.4%. So we think that the true P lives in between those two numbers. Notice how I phrased this. I said I'm 90% confident. I didn't say 90% sure. I didn't say there's a 90% chance. I said 90% confident. And that means that if I repeated the survey 100 times, that I would expect 90 of them to have a confidence interval that contains the true P.